All right, what we're going to do right now is we're going to rigorously define the natural logarithm. So the natural logarithm, and you've seen this before, but to get a real handle on it, we actually have to understand a bit about integration. And now we do know about integration from our Cal 1 class. Logarithm, I gotta spell that correctly for you. And we usually use the notation ln of x. And the way we define it is actually to do the thing we want it to do. We want it to represent the integral of 1 over x, or 1 over t, dt in this case. So the visual representation, I'll give you two. We can look at it and we can take it as the area under the curve, 1 over t, okay, and we're going to take the area of the curve from 1 over t from 1 out to x. Now that makes sense if x is bigger than 1, and that will give us a positive area. Of course, if x is smaller than 1, that'll count as negative area because we're going in the wrong direction. We're going from bigger to smaller. So that's the visual representation. Now the actual graph of natural log of x, as you're familiar with, looks like this. And as I said, there's no area from 1 to itself, so that's going to give us 0 at x is equal to 1. And we'll get negative areas for values between 0 and 1. This is y equals natural log of x. T and y-axis up here. So we've got this nice new function defined for all positive values of x, and it has to be positive values because we can't take the definite integral otherwise. It's just not defined. So let me write that down for all positive values of x. So a couple properties. The first property I'll mention is, well, we can figure out the value of natural log just from this definition for one particular number very easily. Let's make a note that, what would the natural log of 1 be? Well, that would be the integral from 1 to 1. So, you know, it's from 1 to x for x, so we replace x with a 1, and we'll get the integral from 1 to 1 of 1 over t dt. And it's obvious what that is. That's going to be 0, because what are we asking for? Even if we don't know what the graph of y equals natural log of x is from that picture I just drew, we could just take a look at the picture of, it doesn't really matter, any function. If we're asking for the area from 1 to itself, there's no room, there's no area there. So that's why we get that the natural log of 1 is equal to 0. We'll also, you know, eventually go into the fact that, well, e to the 0 has to equal 1, but we're actually going to redefine the exponential function as well in terms of the natural log function. And there's some technical reasons for that that'll be pretty useful for us in proving their properties. Okay, one final thing I should mention, of course, is what is the derivative of this function? Well, let's just note that if I want to take the derivative of the natural log, I mean, we know what it should be, right? It should be 1 over x. But why is that if this is the way that we're defining it? All right, well, we'll take the derivative of the integral from 1 to x of 1 over t dt. And, well, if we're going to take the derivative of an integral, that's what the fundamental theorem of calculus tells us, is that derivatives and integrals basically cancel each other out. Now, what does that mean for us? Well, we've got this x. We're going to plug that x in for t. That's the fundamental theorem of calculus. And so we end up with 1 over x, which is what we'd expect, but it's good to prove that rigorously. All right. Now let's do an example problem, something I might ask you guys to do. So let's say I ask you to use the definition, and I'd probably remind you what this definition is natural log of x equals integral 1 to x 1 over t dt to prove the logarithm property that if you take the logarithm of two things multiplied together, that's the natural log of the first plus the natural log of the second. All right. So, how would I go about doing this? Well, since the natural log is defined in terms of derivatives, integrals, it only makes sense to prove that they're equal using derivatives. So, first thing I'm going to do is prove they have the same derivative. And what do I mean by they? I mean both sides of the equation. So here's what I would do. I'm going to take the derivative of the left-hand side. Oops, excuse me. And this is the harder side to do. And I got to use the definition. So the definition says, it's right up here in the upper right of the screen, the natural log is the integral from 1 to x. But instead of an x, we have a times x of 1 over t dt. Okay, now again, we have this thing with the fundamental theorem of calculus that derivatives and integrals cancel, right? And then the ax would get plugged in for the t. That's almost correct. We would get 1 over ax. What's wrong with that, though, is that the fundamental theorem of calculus only works if it's just a plain old x. The fact that we have the a here as well means that we need to use the chain rule. All right. Chain rule says to multiply by the derivative of the inside. And what's the derivative of a times x? That's going to be just plain old a. Okay, well that's good news because then I can cancel the a's on the top and the bottom of the fraction, and I'm left with just 1 over x. Okay, so what about the right-hand side of that equation? Well, that's even easier. All right, we'll take the derivative of natural log of a plus natural log of x. Split that up, maybe. Natural log of a. I'm probably writing out more details than I need to. But just to make sure it's clear what I'm doing. Plus the derivative of natural log of x. Okay, so now I need to do both of those derivatives. Well, they're both really easy because, well, the derivative of the natural log of a, I have no clue what the number a is, but I do know for a fact that it's a constant, so its derivative is 0. All right, that's all that matters. If you don't see the variable, here's the variable x. I didn't see it anywhere inside of the thing I was taking the derivative of. That must have been a constant with respect to x. That means it has a 0 derivative. And just a moment ago, we already said that the derivative of natural log of x is 1 over x. And so 0 plus 1 over x is 1 over x. And again, they got the exact same derivative. Now, does that mean that they're equal? Almost. Two functions have the same derivative if they differ by only a constant. So what have I proven? I've almost proven everything. I've got the natural log of a times x equals the natural log of a plus the natural log of x, but I also have this possibility that they might be off a little bit, a plus c. could be involved there. I want to show that that c is actually 0. So how do I do that? But c is equal to 0 since when x is equal to 1, I'm just going to plug in 1 for x. So what do I get on the left-hand side? Well, I get a times 1, it's just a. On the right-hand side, I get natural log of a plus natural log of 1 plus c. And then, well, natural log of 1, we already know that that's 0. Okay. And then I can subtract natural log of a from both sides. And what does that leave me with? I've got 0 equals 0 plus c. So c is equal to 0. Therefore, natural log of ax plus natural log of a, equals natural log of a plus natural log of x. And that solves it. I've proven that property of logarithms for the natural logarithm. Okay. What else can we do with this definition? Well, it allows us to integrate 1 over x. We were kind of just told, you know, in Calculus 1 that the integral of 1 over x is the natural log of x, or maybe we weren't. But in any case, often that's taught in Cal 1, that the integral of 1 over x is natural log, but it's actually a little bit more complicated. Let's look at it this way. So now we can integrate 1 over x. So I'll just give you an integration problem involving 1 over x. What would we do? Well, the integral of 1 over x dx. Now the only trick is I can't just say it's the natural log of x because x could be negative. And that doesn't make sense in the natural log. So that's why we throw the absolute value signs around it. Natural log of absolute value x, and again, plus c, since this is an indefinite integral. Okay? That absolute value is important. So, do another example problem. This one's just a straightforward find the integral problem. Find the integral of 3 over x squared minus 2 over x plus 1 plus 4x squared dx. Okay, so when I solve this problem, the first thing I do is either in my head or on paper, I want to rewrite this. I want to rewrite this as 3x to the negative 2 minus 2. I'll actually leave this as 1 over x because we just learned what the integral of 1 over x is. 2 times 1 over x. And then we'll have plus 1 plus 4x squared dx. And now I can go through and just use the power rule. Power rule says, well, first of all, constant multiple rule says I got to bring down that 3. And now for x to the negative, that is a 2 up here. I will take it down, the x, and it's the opposite of taking a derivative. So rather than bringing down and multiplying by the power first, I'm going to add 1 to the power. Negative 2 plus 1 is negative 1. And then I'll divide by that new power. Okay? Then, well, we just learned that the integral of 1 over x is the natural log of absolute value x, so I just have to make sure to remember to bring down that constant multiple, negative 2. The only way I could get a derivative of 1 is from an x. So, I've got that. And then, finally, what about 4x squared? I'll just bring down that constant multiple 4. X So I'm going to add 1 to the power to get x cubed, and then multiply by the reciprocal 1 over 3, or you can think of it as just dividing by the new exponent of 3. And always remember you got to have that plus c there. Okay, but now it's just a matter of simplifying. I've got 3, 1 over -1, that's a -3, and then x to the -1 means I can bring it down to a denominator, minus 2 natural log absolute value x plus x plus, looks like I have a 4/3 x cubed plus a c. Okay, and that wraps up the problem. So now we can do these integrals involving 1 over x terms.